Over the past several years, the term global warming has provided a general description of the state of the environment that could very well evolve due to the influence of human activities on the planet. In years to come, global warming could manifest itself in the form of changing atmospheric and ocean circulation, melting of polar ice sheets, and consequent rising sea level. Scientists concerned with global climate change have been looking for new ways to obtain long-term records of these changes. In the past, they used data derived from tree rings or marine and lake sediments. But these records were limited to short time periods or inadequate detail. Recently, the most accurate records have come from ice cores taken from the polar regions, such as those from the Greenland ice sheet. Greenland, the largest island in the world, is covered almost entirely with snow and ice fallen over the last several 100,000 years. The ice preserves extremely accurate environmental data in the form of trapped gases such as oxygen, carbon dioxide, and methane, ash from volcanoes, and many other chemical indicators of past climate. As these data are analyzed, scientists will be able to develop better ideas about mechanisms that control climate and shed light on vital issues and provide answers to questions. Is the planet really warming due to man's activities? Will these changes affect us rapidly or slowly? What are the mechanisms that control climate? Do we live in an anomalous climatic period? A project known as GISP-2, Greenland Ice Sheet Project 2, has taken a group of scientists and ice drillers to central Greenland each summer, beginning in 1989 and culminating in 1993, to help answer these questions by bringing back the longest continuous ice core ever taken in the world. The project, funded by the Office of Polar Programs of the National Science Foundation, has produced a 5 1/4 inch diameter core that is 3,054.3 meters or 10,021 feet long, and penetrated the entire ice sheet and even into the underlying bedrock. The resultant record covers 2 glacial and 2 interglacial periods of geologic time and goes back more than 250,000 years. Greenland is an island lying mostly above the Arctic Circle between Europe and North America. To get there, the scientists fly with the New York Air National Guard aboard Hercules C-130s. After about 6 hours, the southwest coast of Greenland comes into view. This coast is extremely rugged, and in the summer it has no snow cover. Spectacular icebergs are encountered near the town of Ilulissat, where large chunks of glacier flow to the sea and become icebergs that may drift into shipping lanes on their way south. On the left is the town with about 4,000 people, one of the larger towns on an island with only 60,000 people total. The largest island in the world, most of it snow and ice. At Kangerlussuaq, there's a short stopover before going to the top of the glacier. Here, muskox are commonly seen nearby. These woolly animals, surviving from the last ice age, inhabit much of the area north of the Arctic Circle and probably migrated to northern Greenland 5,000 to 10,000 years ago. Caribou are also seen and graze in the meadows. The glacier, some 10 miles inland, is easily visible. From here, the meltwater flows to the fjord. Everywhere there are signs of the glacier's recent presence, like this polished piece of bedrock. Next, the scientists go on to the camp at the summit, located at the center of the island, flying over the glacier. and the numerous blue meltwater ponds near the edge. The ski-equipped aircraft lands on the hard-packed skiway at an altitude of 11,000 feet above sea level. Looking around the camp from the 110-foot high drill tower, all that can be seen is an utterly flat, endless sea of white. Dr. Paul Majewski from the University of New Hampshire and chief scientist of GISP 2 tells how the project began.
And we're standing right now very close to the site at which we started in 1987. You can see what we had out here. We were landed in a C-130 aircraft, several of us, in order to do the reconnaissance survey for this program. And when we came here, we saw a large, featureless plain. We spent the next several weeks driving 1,500 kilometers around this area using snowmobiles and large Tucker snowcat, sampling at regular intervals in order to find the most appropriate site for drilling what would be, 6 years later, this extremely valuable record. By 1990, it had been decided that we should begin the major component of the deep drilling exercise. And in early 1990, a group of people in April were put in on this site. And by about mid-May, construction began on what we see over here, this what looks like a large blue ranch house. This is what we call the big house, and it serves as the meeting place and also the eating area for the various members of the scientific, drilling, and staff of this camp, which on occasion numbers in excess of about 50 people.
In here, everyone comes in out of the cold, eats, and shares the working day experiences and relaxes. Temperatures outside never go above freezing all summer, and much of the time are even below 0 Fahrenheit. But the cold is offset somewhat because during the field season, the sun is always above the horizon, 24 hours a day.
Over to the left, a little bit farther, you can see a large dome, which is getting progressively smaller with time as the snow begins to cover it up. It was originally a 52-foot diameter dome. It has a 100-foot high tower sticking out of the top, and that's what we call the drill dome.
The drill dome is the center of activity of the project. An overall plan of the drilling and science area shows the location of each function. The drill rig inside the dome, the science trench 15 feet below the surface where the core is processed, with a number of side labs for various disciplines. The dome is unheated to ensure that the core stays at minus 15 degrees centigrade and doesn't melt, which could change its chemical composition. Mark Wumpkes, head driller from the Polar Ice Coring Office, describes how the drill works.
The drill itself is controlled from the surface with this control panel. It has a microprocessor that communicates with a microprocessor in the drill string itself in the instrument package, which is the top portion of the drill. It communicates with that every 300 milliseconds. It reads out all the different parameters we want to, and once the drill communicates that information to the surface, it goes from the control panel to the computer, and all of the drill parameters are displayed on the computer screen so that we can watch everything happening at one time. We have a flux gate magnetometer that can tell us which way the drill is oriented in the borehole, so we can take oriented core. So that's displayed here not in a compass rose, but also digitally. And our load cell, motor current, and drill RPM, the three things that we really watch while we're drilling, are displayed as bar graphs so that you can just at a glance take a look and see how it works. The winch is a hydraulic winch controlled remotely from this panel in the control room. All the controls and gauges and whatnot to show the health of the prime mover are here as well. It's a hydraulic winch. It's driven with a hydraulic pump that's run by a diesel engine. The drill itself is 26.5 meters long, and most of the drill components are about 6 meters long. So and when they're full of core and chips, which we bring to the surface that are a byproduct of the cutting process, it tends to be quite heavy. So we designed a system using a carousel, which is essentially a turntable that has 8 positions in it. And this allows us to have 2 sets of drill components. The drill components that are interchangeable that we have to service when we come to the surface are redundant, and we can reassemble the drill with clean components and then go right down hole without having to spend a lot of time on the surface.
At the end of the 85-foot long drill string is a set of hardened cutters that make a clean cut in the ice and retrieve up to 19 feet on each run. Drill pipe approaches minus 30 degrees centigrade when it arrives at the surface and makes working with it extremely cold on the hands. A specially designed hydraulic winch that holds 13,000 feet of 1-inch multi-conductor cable lowers and raises the drill string for each run. This process continues 24 hours a day, all summer long. On the drill floor, the ice core is extruded from the barrel and measured. Then it's sent down into the science trench 15 feet below, where it's put on the core processing line and rolls from one science station to another. First, the horizontal saw slices pieces that will be analyzed in several side labs. At least half the core is archived to be saved for future investigations. Each scientific discipline gets a carefully controlled section sliced along the length. At this depth, each meter of the core represents about 70 years, or about the length of one's lifetime. So even the smallest portion is highly valuable. The ECM measures the electrical conductivity across the core and can show clearly each year in the record. Dr. Ken Taylor of the Desert Research Institute.
What we're doing here is measuring the electrical conductivity of the ice. We move these 2 small electrodes right here along the ice surface, and we measure how well the ice conducts electrical conductivity. That gets graphed out on a display down here, as right here. You can see peaks, higher peaks where the ice is more acidic, and peaks down here where the ice is more alkaline. The alkaline conditions represent times when there's a lot of dust. And so each one of these peaks here represents an annual layer, much like in a tree ring. And then you can go through and you can count these different layers here, and that helps us to count the core. Other things that also show up on this very well are volcanic events. Large volcanic events would have big peaks up here because they have a lot of sulfate in them. And biomass burning also shows up. Biomass burning pumps out of a lot of ammonia, which neutralizes the core, and it makes a big decrease here in the record. These annual layers in here are the same sorts of annual layers that Tony Gow is looking at visually. And we use the visual stratigraphy and this together to help count the layers more precisely by using the 2 different measurements together in conjunction to get a more accurate record. This is sort of a roadmap to the core. It's our first measurement that we make on the core, and it has the highest resolution, and we can do it continuously along the core. So it provides, in a certain sense, a roadmap for other investigators.
At the next station on the line, Dr. Tony Gow from the Coal Regions Research Lab shows how each annual layer in the core is counted.
Now what we're looking at here is annual layer structure in an ice core from 2,305 meters below the surface of the Greenland ice sheet. I'm going to show you what we mean by winter and summer layers. These, you see a series of white and clear layers. The white layers represent the summer snowfall. The layers